ever look at data and feel like some predictions are way more reliable than others? Like some numbers are solid, others just aren't.
Yeah, that happens a lot in the real world.
Well, today we're diving into a concept that helps explain that, especially in linear regression. It's called homoscedasticity.
Quite a term, right?
It is, but it's really key for knowing if you can actually trust your regression results. We've got our sources lined up to explain what it is, how to spot it, why it matters, and what to do if you don't have it.
Exactly. Think of it like wanting a level playing field for your prediction errors. The uncertainty should be consistent across the board. We'll unpack it.
Okay, so homoscedasticity. Let's break it down. What is it really?
Fundamentally, it's an assumption.
Mm.
In linear regression, we assume the errors, that's the difference between what our model predicts and the actual value, have the same variance.
Same variance across all levels of the independent variable, right? The thing we're using to predict.
Precisely. So if you're predicting, say, has prices from square footage,
Yeah.
homoscedasticity means the sort of scatter or variability around your predicted price should be roughly the same for small houses and for really large houses.
Makes sense. So the opposite of that, heteroscedasticity.
That's it. Heteroscedasticity is when that variance isn't constant.
So sticking with the house example, maybe our predictions for medium-sized houses are pretty good, quite close usually.
Right.
But for the huge mansions, our predictions are like wildly off sometimes, much more spread out.
Exactly that. That increasing spread, maybe it looks like a cone or a funnel on a plot, that's heteroscedasticity. And it causes problems for the standard analysis.
Okay, so how do we actually see this? You mentioned plots. Our sources talk about residual plots.
Residual plots are your best friend here.
Yeah.
Plot the errors, the residuals against the predicted values or against an independent variable.
And what are we looking for? Just randomness.
Ideally, yes.
Yeah.
A nice, boring, random scatter of points around zero. No obvious pattern.
But if it's not homoscedastic?
Then you see a pattern. The classic one is that funnel shape. The points spreading out as the predicted value increases, or maybe they bunch up. Any systematic change in the spread is a visual warning sign.
A red flag. Got it. Like, our confidence in predicting those mansion prices is lower. Are there more formal ways to test this besides just looking?
Oh, absolutely. There are statistical tests. The Broich-Pagan test is a common one.
Okay.
It basically checks if the variance of the errors seems to depend mathematically on the values of your independent variables.
And there's another one mentioned, White's test.
Yeah, White's test is another popular choice. It's a bit more general, can sometimes pick up more complex forms of heteroscedasticity that Broich-Pagan might miss.
Okay, so we can spot it visually, we can test for it statistically, but why is it such a big deal? What breaks if we ignore heteroscedasticity?
This is really the core issue. It makes our standard statistical inferences unreliable. Your confidence intervals, for example.
The range where we think the true value lies.
Exactly. Heteroscedasticity can make those intervals too narrow, suggesting more precision than we actually have, or sometimes too wide, making us miss significant findings. It's like using a stretchy measuring tape.
Okay, unreliable estimates. And what about p-values? The things that tell us if a variable is statistically significant.
They get distorted too.
Yeah.
You might conclude a variable is significant when it actually isn't, or, the other way around.
So potentially making bad decisions based on the model?
Potentially, yes.
Right.
Fundamentally, it violates one of the conditions of the Gauss-Markov theorem.
Ah, okay. Which says?
It says that if certain assumptions hold, including homoscedasticity, then the standard method, ordinary least squares or OLS, gives you the best linear unbiased estimates, the most efficient ones.
BLUE, best linear unbiased estimator.
That's the one. If you have heteroscedasticity, OLS is still unbiased, but it's not the most efficient anymore. Other methods might be better, and the standard errors from OLS are wrong.
Right. So if we find it, what can we actually do? Our sources mention a couple of approaches. Transformations.
Yeah, transforming the dependent variable is a common strategy, taking the logarithm, or maybe the square root.
Why do that?
The idea is to squash the variance, essentially. Applying a function can sometimes make the variance of the transformed variable more constant across the range. It's like rescaling things to stabilize the error spread.
Okay, that makes sense. What about the other option? Robust standard errors.
Robust standard errors are, well, pretty neat. They're a statistical fix that adjusts the standard error calculation to account for the heteroscedasticity.
So you don't change the model itself, just how you calculate the uncertainty.
Exactly. You still use OLS to get your coefficient estimates, but you use these adjusted standard errors to get more reliable confidence intervals and p-values, even with heteroscedasticity present.
Interesting. Now, the sources also briefly touched on machine learning, saying homoscedasticity is sometimes less critical there. Why is that?
Well, in many machine learning tasks, the main goal is pure prediction accuracy on unseen data.
Right, just getting the right answer.
Yeah. While heteroscedasticity might mean the model isn't statistically efficient in the Gauss-Markov sense, if it's still making good predictions, that might be okay for the task at hand. The focus isn't always on precise parameter estimates or p-values like in traditional statistics.
So the prediction can sometimes matter more than the why or the precise statistical properties of the errors.
In some contexts, yes, though understanding error patterns can still definitely help improve models. Even in ML, it's not totally irrelevant.
Okay, let's recap. Homoscedasticity, constant error variance, super important for trusting linear regression results, especially significance tests and confidence intervals.
Definitely.
Its opposite, heteroscedasticity, can skew those results, but we can spot it with plots and tests and deal with it using transformations or robust standard errors.
That covers the main points, which leads to a good question for you, the listener. Real-world data is often messy, right? It rarely fits assumptions perfectly. So how might knowing about homoscedasticity and heteroscedasticity change how you look at data-driven conclusions in your own work or field?
Yeah, think about the uncertainty in your data. Is it consistent? And what does that imply about how much confidence you should place in the statistical models you use or encounter? Something to definitely keep in mind.